Well, good afternoon, ladies and gentlemen, and congratulations on staying the course so far. My talk today is titled Anecdotage. The fact is that there are many stories about mathematics and mathematicians which are great to tell, and I tell a lot of them also in my classes. But unfortunately, many of them are not true, or they are only half true. But nevertheless, they are great stories, and this is what I will regale you with today. Of course, all the stories start with Pythagoras, and there's his famous 3-4-5 triangle, appropriately enough, on a Greek stamp. Now, nothing is known about Pythagoras, so any story you tell about him is likely to be untrue, except to the extent that it was written somewhere about 500 years after his death, if in fact he indeed lived. Now, a number of popular accounts of mathematics state that this fact about the Pythagorean theorem was known in Egypt thousands of years ago and was used by the Egyptians to lay out right angles for the construction of the pyramids. And here is a typical illustration from a very popular maths book called Mathematics for the Million. And there we have the temple architects laying out a right angle. And I must say the perspective in that is very strange. Now, the book is by Lancelot Hogben. He sold many copies, and there he is. Recognize the artist? Irma Stern. And it's in the Irma Stern Museum just down the road from here, although not on display. How did it come to be here? Well, Lancelot Hogben was, in fact, a professor of zoology at UCT in the 1920s for a short period. He is famous in zoological terms for a number of things, but including his work on testing for pregnancy using frogs. He was a pioneer in that respect. Well, the story about the Egyptians using the 3-4-5 triangle has got no authority whatsoever. There are Egyptian manuscripts of 4,000 years ago. You can see one of them up in the British Museum, and none of them has any mention of right angles or Pythagoras or 3-4-5. What a pity. The question is, supposing an Egyptian architect or surveyor said, look, I've got this piece of rope that's 12 units long and it's measured in cubits, and if you break it up into 3 and 4 and 5 and tie knots there and you spread it out on the ground, you make a right angle. How do you know that that angle is a right angle? That's not obvious, because it's quite possible to make triangles of sides of other lengths, such as illustrated there. The 8, 9, 12, so that's 29 cubits. That's not quite a right angle. How do we know? We know because the numbers don't quite match the Pythagorean formula. It's nearly there. That's nearly there as well. And so is that one. But how would you know that those aren't exactly right angles? And how would you know that the 3-4-5 triangle is a right angle if you don't know about Pythagoras? Now, that's a very interesting question, and in fact, I would like to throw it out to mathematicians. How would you prove, without assuming the theorem of Pythagoras or its converse, that a 3-4-5 triangle is right-angled? And I've got an answer for it, but it's not at all an obvious answer. It uses some quite sophisticated geometry. So the myth of the 3-4-5 triangle being used by the Egyptians has got no basis whatsoever. Well, it could have happened that the Egyptians used that 12-cubit length of rope, 3-4-5, 3 plus 4 plus 5 equals 12, to draw up an equilateral triangle of sides 4 each. So there's your equilateral triangle, and then that is most clearly a right angle. Because it's an equilateral triangle, so you've got symmetry, and those two halves are the same, so that's absolutely clearly a right angle. So there's an obvious way of using that piece of rope. Now, the Egyptian surveyors were actually known as, in the Greek, as rope stretchers, because obviously they used rope to lay out their wonderful buildings. Let's move on to Archimedes. Unlike Pythagoras, or indeed Euclid, of whom I haven't said very much, those two figures are totally mythical. We don't know anything about them. Of Euclid, we do know that there's this wonderful book, or 13 books, called The Elements, attributed to him and been into multiple editions and revisions over the centuries. So of Euclid, that much is known, but nothing is known about Euclid. There are some anecdotes about him, that he worked in Alexandria in Egypt, and that he was once approached by the Ptolemy, the pharaoh, to say that, look, Euclid, this is all very well, but I want an easy way to learn geometry. And Euclid said rather haughtily, "O king, there is no royal road to geometry." It's a nice story, but unfortunately that same story is told of Alexander the Great when he was being tutored by Aristotle, or one of his other tutors. But moving on from Pythagoras and Euclid, the next great name is Archimedes, and in the case of Archimedes, we know a great deal. Simply because he was unfortunate enough to die in the siege of Syracuse by the Roman general Marcellus. This was during one of the wars against Carthage, the Punic Wars, and the historian Plutarch gives an account of the life of Marcellus, in which the siege of Syracuse is mentioned, and Archimedes is mentioned, and lots of anecdotes are told about Archimedes in this context. Plutarch relates many stories, many of which have more fancy than fact. For example, although the Greeks certainly knew about burning mirrors, if your mirror is slightly concave, you can use it to focus light and burn things. The story that Archimedes used burning mirrors to set fire to the Roman ships in the siege is, I think, rather fanciful. There have been several unsuccessful attempts to replicate this achievement really convincingly, famously in the TV program Mythbusters. However, the story of the counterfeit crown is interesting because it's sort of half true. The king of Syracuse had commissioned a goldsmith to make a crown for him. And he gave the goldsmith a lump of gold and said, "Make a crown." The goldsmith then came back with the crown, but the king was a bit suspicious that the goldsmith had adulterated the gold with some silver. You can't really tell the difference by looking at it, and had been able to keep the gold, the silver being, of course, relatively inexpensive. So the king consulted his court mathematician, Archimedes. Archimedes realized that the key was to determine the density of the crown and compare it with the density, that is the ratio of weight to volume. mass divided by volume. The story goes that Archimedes worked out that he could measure the volume of the crown by its displacement of water in a tub. And then he could measure an equal weight of gold the same way, and if the displacements were the same, that was fine. And if they weren't, something had gone wrong. And he realized this in the bath. And the story of Archimedes in the bath goes down the generations. Now, the first thing to say is that the crown was not like that. That's a European crown. The crown was probably a wreath of laurel leaves, so probably quite a lightweight affair, not very substantial at all. Well, Archimedes is said to have leapt out of the bath with such joy at thinking of this idea of using displacement of water to measure the density of the crown, and ran down the streets of Syracuse naked, crying, "Eureka, Eureka, I have found it." But here's a problem. You've got, let's say the crown was but even half a kilogram is quite a lot. Now gold is very heavy, and half a kilogram of gold is about the size of a bar of chocolate. Now, if the crown was of that weight, the amount of displacement in a tub of water, and it's a crown, so you need quite a big tub of water to measure the change of height of the water, it's not going to be possible to do that and compare it with the same weight of pure gold. So that version of the story is a bit naive, but it's probable that Archimedes was far more subtle than that, because he had discovered not just this business about the density, which made him leap out of the bath, but the concept that when you submerge something in water, it loses weight by the volume of water that's been displaced. So, you take your kilogram or half kilogram of pure gold, which is exactly the same weight as the crown, and you measure them on a balance, but each pan goes down in a tub of water. So if they balanced exactly, you would know that the crown was pure gold. But if the crown came up a bit because it had been adulterated with less dense silver, it would unbalance. That you could then weigh the crown against a different mass of gold. You could actually do a precise calculation when you've got the right weights and work out by what percentage the goldsmith had adulterated the crown. And that is worth shouting Archimedes for. He's also remembered, of course, for having died in the siege, which is a bit of a sad story. He was quite an old man then. But the idea of Archimedes running down the streets of Syracuse has caught our imagination and led to a little clery-hue. Now, clery-hues are an insufficiently admired form of poetry. Archimedes of Syracuse, to get into the news, cried out "Eureka!" and became the first streaker. Well, Archimedes is also correctly remembered for his estimate of the value of pi. The Cambridge Undergraduate Mathematics Society is called the Archimedeans, and they publish a journal called, appropriately, Eureka, and in that journal appeared this verse. Actually, I don't know if the Archimedeans as a society ever sang it. Apparently it has to be sung irreverently to the tune of the church's one foundation, and goes, "All praise to Archimedes, who waved the royal hat, displacing courts of H and C upon the bathroom mat. For that unending decimal we mortals know as pi, he found that 3 1/7 is just a bit too high. Well, staying in Cambridge, we come to the second of the 3 top mathematicians of all time, the first being Archimedes, and the second one is Isaac Newton. Now, anybody who goes to Cambridge, crosses over the bridge at Silver Street and looks back at that wooden bridge. And if you're getting a punt ride, the polar of the punt, if he's a professional, will be telling stories about Cambridge, some of which are true, and some aren't. But he will say, that's Newton's bridge, Isaac Newton's bridge. It was designed by Isaac Newton with a very clever geometrical design, which seemed to stand up without nails. Now, this is outside Queen's College, or linking the 2 parts of Queen's College across the river. And the fellows, the dons of Queen's College, were quite intrigued. How could this thing stand up without any nails in it, just the joints? So they decided to take it down and examine it to see what the secret was. And when they tried to put it together, they couldn't, and they had to use nails. That's such a nice story, but it had nothing to do with Newton. Newton was not a student of Queen's. He was a student and later a fellow and Lucasian professor of mathematics at Trinity College, further down the river. And the bridge was built in 1749, over 20 years after Newton's death. The original bridge indeed had pegs securing it, but the pegs were from the outside. So if you were crossing the bridge, as the dons might have, you couldn't see any pegs, because the pegs were only from the outside into the joints. So that's where the story seems to come from. But you just have to look at the heavy beams of this. And the interesting engineering feature of this bridge is that it's built with straight beams, even though it has this nice, gentle curve. These are straight beams. And interesting engineering principles in design here. But these are long chunks originally, I think, oak. Imagine a bunch of elderly dons of Queen's College coming and trying to take this bridge apart. No, I don't believe the story. The bridge, however, has been repaired more than once in its time. In, I think most recently, 1905. And because some of the joints, and this being wood, some of the joints had deteriorated and the bridge became unsafe. When it was rebuilt with new timbers, and at that time they used teak and not oak, they put in great big iron nuts and bolts to fasten the joints together as security. So only a pedant could say that the bridge was built originally without nails. The bridge nevertheless has mathematical interest. The gentle curve underneath the bridge is given by an elegant arrangement of dead straight timbers. Any sort of curved timber would have weakness, so you build it of straight timbers. And mathematicians called curves generated by the straight lines in this way, they call them envelopes. The bridge was designed by a man by the name of William Etheridge and built by James Essex, as I said, in 1749, and it's been rebuilt, as I said. It deserves the name, therefore, mathematical bridge, by which it is actually known, but not Newton's bridge. Here's an example of a bridge built by the same man, Etheridge, far more elaborate bridge. It used to go over the River Thames at Walton, And the artist, Canaletto. You can see that just from the very precise geometrical site. And the man here is supposed to be the designer. So, unfortunately, that bridge didn't seem to survive and was taken down after about 30 years. While the Newton Bridge story is in fact a myth, many other stories about Newton are genuine. He did indeed get his idea for the theory of gravity by observing the fall of an apple in the orchard in his family home in Lincolnshire. This was a very fortunate forced absence from Cambridge in plague years. He went back home to get away from Cambridge, where plague was running wild, and spent a year or so in Lincolnshire, where he was born, on the farm, his farm, and in his family home. And that's where he conceived the idea of the falling apple, falling under gravity, and thinking of the moon. And the moon is also falling under gravity, except that it's got a horizontal motion as well, so that's what keeps it in orbit around the Earth. It's falling toward, if there was no gravity, the moon would go off in a straight line. But gravity keeps it in orbit. And Newton came up with the theory that this was how gravity works, and also the inverse square law, which is, of course, to say that the moon and an apple are falling towards the Earth in the same way is, okay, interesting. But when you make it precise in terms of the inverse square law and other factors, that is where the mathematics and physics comes in. The cartoons and legends about the apple falling on Newton's head under the tree are simple embellishments. And I like reciting at this stage a stanza composed by Byron, no less, from his long poem Don Juan. When Newton saw an apple fall, he found in that brief startle from his contemplation a means of proving that the earth turned round in a most natural whirl called gravitation. And this is the sole mortal who could grapple since Adam with a fall or with an apple. Very clever little poem by Byron, whose daughter, by the way, Ada, is known for her major contribution to computer science. Ada Lovelace was a daughter of Byron, who teamed up with the mathematician Charles Babbage and wrote the first treatise on what is now regarded as computer science, because Babbage was designing these wonderful calculating machines. You can see his designs in the Science Museum in London. An interesting connection is often remarked about the death of Galileo, the first modern scientist in many respects, and the birth of Isaac Newton. It is said that Galileo died and Newton was born in the same year, 1642. It's a nice numerical coincidence, but it's actually not quite correct. They were both born, well, Galileo died in 1642 and Newton was born in 1642, but at that time, 1642, Italy and England were not using the same calendars. Italy had followed the Pope, Gregory, in 1582, and they'd revised the calendar from the old Julian to the Gregorian calendar. But Protestant England had fiercely resisted this piece of popery and still used the old Julian calendar, which lagged 10 days behind the Gregorian, and that's the source of this quibble. In the Gregorian calendar, the death of Galileo was 8th of January 1642, and the birth of Newton was the 4th of January 1643. But on the old calendar, Newton, famously born on Christmas Day, 1642, but Christmas Day 1642, was actually in the Gregorian calendar the 4th of January 1643. So these 2 years don't quite fit together. However, it is true to say that Newton died within 365 days of the death of Galileo, which is sort of interesting, but the 1642 coincidence doesn't work. Incidentally, I was quite interested thinking about this way the calendar had to be adjusted, and I've given a talk in the summer school a few years ago exactly on this topic. England only adopted the Gregorian calendar under some protest in 1752, much later than it was, that is 1582 to 1752, that's quite a long time, and afterwards, but they eventually saw the logic of the Gregorian calendar, so they changed, which meant they had to adapt their calendar by 11 days, which, by the way, explains why the British tax year doesn't end on the 25th of March, which used to be New Year's Day in the old calendar, but it's on the 5th of April, 11 days. So that's why the British tax year ends on that curious day. But that's getting away from this. I often wondered, what happened in South Africa? Well, of course, the Dutch came here, and they would have had a calendar, and the Dutch being Protestant, I wondered, what calendar were they using? Well, I found the answer to this was to actually look at the diaries of Jan van Riebeck, which will say, give dates and days of the week, and then compare his diaries with the corresponding dates in another famous diarist, or more famous diarist, namely Samuel Pepys in England. And then you find that the Dutch had adopted, in 1652, they'd already adopted the Gregorian calendar. So at no stage did South Africa have to adjust calendars from the old Julian to the Gregorian. But there's one other genuine coincidence related to this story. Exactly 300 years to the day after the death of Galileo, Stephen Hawking was born. 300 years exactly to the day after the death of Galileo. And this he rather proudly tells us about in his various writings. This next story is not a mathematical myth, but because it's got a lot to do with gravity, I can move smoothly from Newton into a story about the American space program. Now, anybody who does crosswords in bed must know that after a couple of words, your ballpoint stops writing, and you have to shake it or hold the point downwards to get the ink flowing again. So when the Americans were planning to send men into space, they realized that the astronauts would have to make notes. And they didn't have nice little tablets and things like that in those days. And that ballpoints would not operate in zero gravity. So they called for tenders to solve this problem to create a zero gravity ballpoint. Now, it's actually not all that difficult to solve that problem. What you've got to do is create a pressurized cartridge of ink in your ballpoint. Most cartridges of ink aren't pressurized, but if you have a pressurized one, it will write at all angles. Well, they spent a lot of money, so the story goes, on solving this problem. Meanwhile, the Russians, it is said, solved the problem in a different way. They gave their astronauts pencils. Well, it is a great story, but actually it's certainly untrue. It would be extremely dangerous and unwise to take a pencil into space, because that point breaks. It floats around. It doesn't fall on the floor. It floats around. It could get into your eye. It could get into any of the sensitive instruments there. So you certainly would ban anything in the capsule of that nature. In fact, the Russians bought the American pressurized ballpoints from the Americans for their cosmonauts. So that's again a nice story. Incidentally, just this week, it was announced in the Sunday Times, I saw it, that a certain astronaut, John Young, who flew to the moon twice, we don't remember him very well, of course, he died this week. He's famous for receiving an official reprimand for smuggling a corned beef sandwich onto the Gemini spacecraft. A stray crumb from his snack floating around in the Gemini capsule could have destroyed that mission. So this principle of the using a pencil is just not on. Staying with gravity, and another nice story, it is often said that when you pull the plug out of your bath, nobody's using baths these days, so let's suppose you from your hand basin, and you don't, no, never mind. But if you pull the plug out of your bath, the water will go around that way in the southern hemisphere and that way in the northern hemisphere. They go around in different ways. This is said to be due to the Coriolis effect. Now, the points on the equator are moving fastest around the world. So anything north of the equator will move a bit more slowly than the equator, so you get that sort of movement, which is observed in wind patterns and also ocean currents in the northern hemisphere in general. Whereas in the southern hemisphere, with the equator moving the fastest, points south of the equator are moving a bit more slowly, so they go around this way. Clockwise, anti-clockwise in the... no, by the way around. Clockwise in the northern hemisphere and anti-clockwise in the southern. Well, the people often say that they observe this effect. Clockwise south of the equator and anti-clockwise north of the equator. Well, there's regularly discussion about how this Coriolis effect, which is genuine in the context of macro situations like ocean currents and airflow, would it have an effect when water runs down a plug hole? And the answer is, of course not. On a small scale, that very small Coriolis effect is dwarfed by other factors. Principally by the way the water was swirling around before you pulled the plug out, or the shape of the basin, or any breeze that was growing across the water surface caused by a stray butterfly, for example, or by temperature differences in the bathroom causing convection currents that way around in the water. all of those effects would dwarf the Coriolis effect. However, if all those factors are taken into account and carefully eliminated, the Coriolis effect can be observed. And this was done, nearly 50 years ago. First, you must build a large, perfectly circular tank, about 2 meters across and 15 centimeters deep, with a very precisely drilled small plug hole at the bottom. Fill the tank with water, cover it, and let it settle for a day or two. The apparatus must be in a sealed, windowless room at an even temperature. Next, you have to be careful about the way you pull the plug out. You can't just yank it out on a chain. You've got to pull it out from the bottom very carefully. And if you do that with as little disturbance of the water as possible, and this was done by a professor of fluid mechanics at MIT, the Massachusetts Institute of Technology in America, a man by the name of Asher Shapiro. His tank took some minutes to empty, and no vortex was initially noticed. But at the end, the water went out anti-clockwise every time. So under those very strict experimental conditions, the Coriolis effect does affect the water going down the plug hole. Shapiro published his paper in Nature describing his experiment, and that inspired a group of, at the University of Sydney in the Southern Hemisphere, to repeat the experiment a year or so later. And they did exactly the same thing, and they confirmed that under the same circumstances, the water ran out clockwise in the Southern Hemisphere. Well, there's no record of this experiment being performed on the equator. However, I've read that somewhere in Ecuador, which of course is the country through which the equator runs, there is a tourist attraction where visitors are invited at a fee to observe the Coriolis effect in 2 tanks in a room, in which the tourists are told is astride the equator. There are 2 tanks carefully positioned on either side of the equator. The tourists are then shown how the water runs out anti-clockwise in the northern hemisphere, in the northern tank, and clockwise in the southern tank. Well, you can believe that. And I've often thought, what a good trick to pull. There are not many areas that sit on the equator, but one place where this could be set up as a tourist attraction is Entebbe in Uganda, which sits on the equator. It would be a good place to build exactly a replica of that Ecuador attraction. And if the Department of Physics of the University of Uganda, Entebbe, doesn't do that, maybe their Department of Tourism should. They might earn some money. Well, if you believe the Coriolis effect takes place in the bathtub and you run the experiment repeatedly at home to show that the water runs out for us clockwise, you may expect to be right half the time, and the other half the time you can give to experimental error. But talking about clockwise, why do clocks go clockwise? Who decided that clocks should go around that way? To be sure, I'm not sure that there's really a definitive answer to this, but there are various stories. Now, if you're in the northern hemisphere, so I'm then facing south, in the northern hemisphere, the sun rises over there and goes round am I seeing that correctly? Yes. The sun rises and goes around that way. However, they were telling the time by means of a sundial. So if they have a sundial with a vertical gnomon there, and the sun goes around like that, the shadow of the gnomon will go around in the clockwise direction. So perhaps that's why clocks were designed to mimic the sundial. So that's a nice story, but it doesn't quite work, because apart from sundials on the ground, in many cases, sundials, like clocks today, are put up on the wall of a building so that the public can see the clock. So now we've got the clock going around, and this is a sundial from Queen's College, the same college which has the mathematical bridge. This is a sundial in Queen's College, and of course it faces south. But this time, because the gnomon of the sundial is pointing out, the shadow of the gnomon will go that way around. The sun is going that way around, and the shadow goes that way around. This, by the way, is a very sophisticated sundial. It also can observe the shadow of the moon, and you can tell the time using that. A very sophisticated and complicated sundial, which is said, of course, to have been designed by Isaac Newton, which it wasn't. But still, it's a good story. So the vertical sundial does not support the clockwise story. And after all, astronomers looking up at the pole star, for example, would see things going around that way rather than the other way. There's a wonderful word for clockwise, instead of anti-clockwise, widdershins. Widdershins is regarded as the unnatural movement. So clockwise is that way that's natural. It's the way we turn a corkscrew, for example, and it's a right-hand rule in many respects. So is there a rational reason for clocks going clockwise? Early clocks, in fact, sometimes went clockwise and sometimes widdershins. Then eventually the design settled down, and probably the successful clockmakers had their designs followed. And the successful ones were the ones where the clocks went round clockwise, of course. But here's a famous clock. Oh, I wanted to say something about the digits on a clock. Have you noticed they all use Roman digits, of course? And all clocks use 4 strokes for 4, not the IV option. I don't know why, but they don't use VIII for 9, they use IX for 9. So this is a famous clock. Where? Stands the church clock at 10 to 3, and is there honey still for tea? Rupert Brooke's famous poem, Grantchester. In visiting Grantchester, I must say this is not relevant, but the War Memorial in Grantchester of the First World War is very moving, as all war memorials are, but the inscription is another line from Rupert Brooke, who died in the First World War, and the inscription is simply men with famous hearts. And that's a line from Grantchester. Well, getting on to one of the nice myths of mathematics that I enjoy, it concerns Nobel Prizes. There's the Nobel medallion. Alfred Nobel left his considerable fortune to creating prizes for physics, chemistry, medicine, literature, and peace. The Swedish Academy of Sciences awards the first 4 prizes, while the Peace Prize is awarded by a Norwegian committee. In 1968, the Swedish bank, the Riksbank, endowed a prize for economics to celebrate the bank's 300th anniversary. And they somehow or other got people to accept it as a Nobel Prize as well. Some purists say it's not a real Nobel Prize. But there's no Nobel Prize for mathematics. The story goes that when Nobel was deciding on the category for his prizes, maths was an option. He asked his advisors who might be a winner of a maths prize. At the time, the top Swedish mathematician was a man by the name of Gustav Mittag-Leffler, who had incurred Nobel's displeasure by running off with his wife. Prejudiced against Mittag-Leffler and against mathematicians in general, particularly horrified that Mittag-Leffler might win his prestigious prize, Nobel decreed, "Let there be no Nobel Prize for mathematics." It's a lovely story. Trouble is, Nobel wasn't married. Well, you then modify the story to a mutual acquaintance of Nobel, a famous woman mathematician called Sonia Kovalevskaya, of which there are also many interesting stories. She was, let's say, an advanced woman and very attractive, as that portrait shows, and that she is said to have been stolen from Nobel by Mittag-Leffler. But there's no evidence, in fact, that she had a liaison in any sense with either of those two. So these stories must be repeated because they're so nice. But there's no authority for either of those versions. The real answer is rather simple. Nobel wanted his prizes awarded to people who had provided the greatest benefit to mankind. Maths in the 19th century was regarded as far too theoretical a topic to have a prize. So they didn't even think of awarding a mathematics prize. And the mathematicians were not too fussed about this. They thought that if you created this mathematics prize, it would generate far too much animosity between mathematicians competing to win the prize. And a famous British mathematician, G.H. Hardy, boasted that the mathematics he worked on, prime numbers, had no use whatsoever. And he was proud of it. So he would not have wanted to have been the recipient of a prize which provided great benefit to mankind. Ironically, Hardy's work on prime numbers has turned out to be of great importance in these days because prime numbers are the cornerstones of encryption methods, these so-called unbreakable codes. Anyway, so there's no Nobel Prize for mathematics. However, in 1936, a Canadian mathematician, Charles Fields, endowed what is called today the Fields Medal for an outstanding contribution to mathematics. There's the Fields Medal, both sides, which has got some interesting features. Never mind the Latin around the outside. This is supposed to be Archimedes, but that's totally fanciful. There's no bust or portrait of Archimedes. And the other thing, you can't really see it, unfortunately, here, but there's a date here where, and it's written in Roman numerals, makes sense, except that the engraver used an N instead of an M in the date. Anyway, the Fields Medal is often called the mathematician's Nobel Prize. However, it's not really comparable in most ways. A Nobel Prize is currently worth about $1 million. The Fields Medal is worth about $15,000. Secondly, The Fields Medal is for a youthful contribution to mathematics. In order to win it, your work must be done before you reach the age of 40. It cannot be awarded to a mathematician over the age of 40. And thirdly, it is not an annual award, but only given on the occasion of the 4-yearly International Congress of Mathematicians. So, you have a Fields Medal. It is very highly regarded in the mathematical world. If you win a Fields Medal, you can command whatever salary you like, I think, from your university. And the people who have won Fields Medals have gone on to do certainly wonderful things. However, since 2003, there has been a genuine mathematics version of a Nobel Prize. It's called the Nobel Prize. Now, I mentioned Niels Bohr yesterday. He was the young mathematician who showed that it's not possible to produce a solution formula for the fifth degree equation. And that was in the early 19th century. And so he's Norwegian, and the Norwegian government decided to put up a big prize, namely equivalent to the Nobel Prize, to be awarded every year for a major achievement in mathematics on the same basis as the Nobel Prize. And it was established in 2001, first awarded in 2003. It's worth 6 million Norwegian kroner, which is about $1 million American. And the closeness of the name Nobel to Nobel is just a fortunate coincidence. Well, while there's no Nobel Prize for mathematics, on several occasions the Nobel Prize for economics has been awarded for work which was essentially mathematical. A good example is the mathematician John Nash, who won the Nobel Prize in economics for his work in game theory, which is a mathematical theory which has very important applications in economics. I think that picture shows that Nash was in fact a tragic figure. After a meteoric rise in the mathematical world, he descended into the depths of schizophrenia for 30 or 40 years. Emerging from the abyss, he was awarded a Nobel Prize in economics in 1994. Then he won an Nobel Prize for his work in mathematics in 2015. Tragedy pursued him. Returning from Norway to America and driving with his wife from the airport in New York to home, he was involved in a car crash and both of them were killed. Well, the Nobel Prize in economics was awarded to other people for essentially mathematical works, but there is a better example of a Nobel Prize for mathematics which is closer to home. And that is the Alan Cormack, who was a lecturer in physics at UCT in the 1940s and early 50s, working in crystallography and moving on to working in atomic physics. He was born in Johannesburg in 1924, studied physics at UCT, graduated with a master's degree in crystallography, working under the famous physicist R.W. James, after whom the James building on campus is known. James, by the way, was one of the famous Shackleton party, which nearly perished in an ill-fated expedition to Antarctica. But at the time, James Cormack, having worked in crystallography, which involves a lot of X-ray work, was asked to go and look after Grooteskier's X-ray material, because nobody at Grooteskeer understood X-rays, apparently. So he was asked to go and curate the work on X-rays. And it was there that he came up with this idea of X-ray tomography. And this was in 1956. He conceived the idea of an X-ray. Now, if you take an X-ray from there to there, you encounter just bone from there to there. And any soft tissue in the middle is masked by bone. So you can't take an X-ray of the skull. However, what Cormack realized is if you take multiple X-rays with parallel lines through a slice there, then move your X-rays around that way and measure all those X-rays attenuation from different points across the skull, you'll get a lot of readings, all slightly different, and you then should be able to work out different densities for the soft tissue inside the bone. And that's what X-ray tomography is all about. The word comes from slice, the Greek word for slice, tomos. And he conceived that idea. The problem was that you could do all these measurements and you'd get this fantastic amount of information. But this was 1956. How did you solve it? Well, theoretically, he knew what he could solve, how he could solve this, because this involved something called a radon transform, which, let me write some inscrutable maths here. It's an integral, line integral over a line integral, just like that. You knew what these lines are, and you know what the result of this is for all these different lines. Can you work out the function f, which is the density function of what's inside your head? Well, 20, 30 years later, an engineer in England, Geoffrey Hounsfield, came up with this idea by then, and he developed a program to crack this and to show how you could actually invert that radon transform, discover the function f, which then gives you a picture of the brain, and you can pick up brain tumors in that way, and of course for other parts of the body as well. So for that reason, everybody thought that he deserved a Nobel Prize until they discovered that Cormack had thought of this 30 years earlier. So Cormack and Hounsfield were awarded the Nobel Prize for medicine at the same time in 1979. So this is a Nobel Prize for medicine awarded to a physicist and an electrical engineer for a piece of work involving mathematics. When they went to the ceremony of the presentation, Cormack commented in his acceptance speech that he was a particle physicist and Hounsfield an electrical engineer, and what they knew about medicine jointly could be easily written on one sheet of a doctor's prescription pad. Well, apart from the Nobel Prizes for Peace and Literature, 4 Nobel Prizes for Science have been awarded to South Africans: Aaron Klug, Max Tyler, Alan Cormack, Sidney Brenner. And of course, we've had Nobel Prizes for Peace and Literature. But apart from Cormack, all those other Nobel Prizes for physics and biology and so on, they were all won by those scientists for work that they did after they'd left South Africa. So Cormack is the only one to have been awarded, only South African to have been awarded a prize for work that he did in South Africa. another little pebble. The word tom in tomography comes from slice, and atom means something you can't slice. Here's a nice quiz question. There's an English word that begins with TM. Nobody would believe it until you look it up in the dictionary, and the word is tmesis. And it describes something that's used quite a lot in slang, where you take a word and you insert something in the middle. So you don't say absolutely marvelous, you say absolutely marvelous. You slice the word up and put it in. Einstein, of course, won a Nobel Prize in 1921, not as you might expect because of his theories of special and general relativity, but because of his work in, it turns out, in the photoelectric effect. The Nobel Prizes, they didn't at that time believe that relativity was quite relevant to the benefit of mankind. There's a lovely anecdote about Einstein. He was working in the patent office in Bern, as everybody seems to know, and at that time the makers of Toblerone chocolate designed this new packaging and had a special recipe involving chocolate and nougat, and they submitted it to the patent office for patenting, and it is said that Einstein signed the patent for Toblerone chocolate. It's a good story, but by that time Einstein's work had been recognized and he had moved on to other things. He'd been recognized, and anyway, Einstein was doing electrical, mechanical gadgets, not chocolate and recipes. It's often said about mathematics, there are categories of people, famous people, who were duds at mathematics. And here's one that I rather enjoy. I had a feeling once about mathematics that I saw it all. Depth beyond depth was revealed to me, the abyss and the abyss. I saw, as one might see the transit of Venus, or even the Lord Mayor's show, a quantity passing through infinity and changing its sign from plus to minus. I saw exactly how it happened and why the tergiversation was inevitable, and how the one step involved all the others. It was like politics. But it was after dinner, and I let it go. Who's that? Winston Churchill, of course. The word tergiversation gives it away. Only Churchill would use that word, and only for Churchill, of course, practiced tergiversation in his politics. But Churchill was actually quite friendly towards mathematicians, and he wrote, there he is as a young man, he wrote a little bit about mathematics and how important it was. He had actually studied up mathematics and had passed the entrance exam into Sandhurst, so he could actually do trigonometry and things like that. But after getting into Sandhurst, getting admitted to the army, he had an admiration for mathematics, as described there. And in fact, some years later, he played an important role in encouraging mathematicians like Alan Turing, of code-breaking fame, and famously, Churchill wrote a memo, just see that they get their money that they wanted, and advise me when it has been done. And of course, Turing and his code-breakers played a very significant part in World War II. Well, I think it's time to end. My final anecdote needs some background. Tom Lehrer was a famous man in the 1950s, certainly among students. an absolute whiz at mathematics, got into Harvard, I think, at age 14, got a master's degree at age 15 or 16, and then got distracted into songwriting and musicals. I gather he's still alive. I was checking him up. He would be 90 now. He wrote many popular songs, and some of them have a mathematical flavor. My favorite is a parody of the Gilbert and Sullivan patter song from Princess Ida, If You Give Me Your Attention. And let me give you that song. There's no particular tune to it as being a patter song. If you give me your attention, I will tell you what I am. I'm a brilliant mathematician, also something of a ham. I've tried for numerous degrees. In fact, I've one of each. Of course, that makes me eminently qualified to teach. I understand the subject matter thoroughly, it's true, and I can't see why it isn't all as obvious to you. Each lecture is a masterpiece, meticulously planned, yet everybody tells me that I'm hard to understand, and I can't think why. And at this, of course, in the Gilbert and Sullivan, the chorus goes, he can't think why. And then the chomp, ka-chomp, 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 the orchestra goes into the second verse. My diagrams are models of true art, you must agree, and my handwriting is famous for its legibility. Take a word like a minimum, to use a random word. For anyone to say he cannot read that is absurd. The anecdotes I tell get more amusing every year, though frankly, what they go to prove is sometimes less than clear. And all my explanations are quite lucid, I'm sure, yet everybody tells me that my lectures are obscure, and I can't think why. He can't think why. Consider, for example, just the force of gravity. It's inversely proportional to something, let me see, it's r cubed